in the old days, we would be sitting around a table and going around and introducing ourselves until the group got so big that we couldn't do that anymore. And so, anyway, I am looking forward to sitting around a table with everybody. But in the meantime, we get to have people from all over, like Passive House, Alberta, I saw. Hello, people far and wide, and welcome. I'm Tom Bassett-Dilley. I'm one of the board members here at Passive House Alliance Chicago, which is now called Phius Alliance. We're, with the rebranding, kind of getting used to saying it's the new way. We had a great time at the Phius conference, PhiusCon in Tarrytown, New York, and presented a slightly more condensed version of this talk that I'm going to do here tonight on retrofit. So I'm excited to share that. So without further ado, I will share my screen and get this thing rolling here. So I want to talk about residential retrofits, and these are single family projects that we're in the process of doing right now in our office. Some are partway completed, some are near completion, some are on a 5-year plan. So on all of these, we're learning a lot. And one of the things that I learned in doing this was really that that the Passive House metrics as they currently stand, I'm running into problems with it. So I thought, well, I should kind of share that and figure out what the problems are and if we should help kind of rethink the approach. Because the big picture is what I'm talking about on this slide, that embodied carbon is really, really important. And embodied carbon, of course, means the energy that's in a building as it exists today. If you were to tear it down, you'd spend energy tearing it down. You'd spend a lot of energy making new materials to build a new building. Whereas if you retrofit it, you use just a few you use much less materials and use a lot less energy. The big thinking, of course, being that if we just tore down all of our leaky, uninsulated buildings and replace them with passive houses, we'd have such a huge spike in carbon consumption that we'd really be going against our goals, which is to reduce carbon consumption. So it's funny because when I, went into architecture, it was all about designing buildings and new buildings. So exciting. And, the first passive house projects we did were new. And, figuring out how you do your air sealing details and thermal bridge avoidance and all that stuff is challenging enough on a new project, but when you do it on a retrofit, it's even more. So I was, really focused on new buildings, but now personally really focused on existing and retrofit. So this particular slide we did using there's a Frank Lloyd Wright house that we're retrofitting right now here in Oak Park. And we used some data from some studies on how much embodied energy is in materials and buildings, and tried to figure out, like, well, what if, we tore down a building like this and replaced it? Not that we're talking about tearing down a Frank Lloyd Wright, but theoretically, okay. And so I've collapsed a lot of data onto this slide, but on there's a kind of a medium blue line that goes way up and then across, and that's like if we were to demo and rebuild, a net positive 10% building, you can see that that would take a lot of energy up front. And if you look at that compared to doing nothing to the existing house, it would be like 9 years of energy consumption in the house before you would recapture that energy. So if you just did low-hanging fruit, just minor stuff, some air sealing, a little bit of insulation, you're talking about a 16-year energy payback. It's not a money payback, it's an energy payback. And so it's really hard to defend the idea of tearing down a building which is structurally sound if you can retrofit it. And so the blue line towards the bottom is what we're trying to do on this building, which is retrofit it to net zero. So it takes some energy to do that. We have new mechanical systems, but eventually we would have had new mechanical systems anyway. We're adding insulation. That's a good thing to do no matter what, because there was almost none in there. And so you can see it takes a small amount of energy to to get there, and then you're leveled out. So so that's where we want to go. So retrofits are really key. Click back on this so we can advance. There we go. And this is what we're looking at in most of the region. You know, here's a typical Chicago 2-flat. This is a project we did a retrofit on. And these buildings are mostly uninsulated. They're really leaky. There's a lot of air movement through them, especially up through the roof. They typically have inefficient fossil fuel HVAC, like 80% furnaces or boilers. And so most of the energy that gets to this building is wasted. It's just blown through the walls and the leaky windows and leaky roof. And when we start to energy model it, which we do with about all of our projects, you can see this little graph here next to the wireframe of the building, showing that most of the energy goes to just heating this thing. So it keeps the bricks dry, but it's there are other ways to do that. So we want to figure out, you know, how we're going to get there. When we look at the scale of this problem, these are the kind of sobering or exciting numbers, depending on how ambitious you're feeling. You can go online and look at residential data that Chicago has, and look at how much energy people are using. You know, about 4.2 billion kilowatt hours in the city, and using about 695 million therms. And if you convert the therms to kilowatt hours, you see that your kilowatt hours per person using the population data is about 9,000 kilowatt hours per person per year. And the Phius source energy target is about a third of that. So so we're talking about like a 63% energy reduction per person. And that's as we move to like electric cars charging at our houses. So instead of using that energy, sort of consuming that energy at a gas pump, you're consuming some of that energy at your house. And so it's a lot. To me, I don't see the idea that we're just going to switch from gas to electricity and solve the problem, because that would probably mean building new power plants. We're going to have to make our buildings more efficient while we switch fuels. So if you look at, okay, so 63% is like getting us to Phius source energy target, but what about the Paris Accord? Well, that's 80% emissions reduction by 2050, zero by 2100. And of course, there's the Architecture 2030 challenge, zero carbon buildings by 2030. If you look at Chicago metropolitan area planning, there's 3.37 million housing units in Chicago metro. And if like a third of those are replaced and we only have to retrofit about 2 million units, well, that's like 609 per day for the next, to get to 2030. So it's really daunting. If we give ourselves to 2050, it's only about 189 houses per day. So we got, a lot of work to do. And so here's, Thursday in 2039, there's 189 houses. So think about that, what that means for local jobs if you actually get people doing this. Now, each building does not need to be done in one shot. We can do pieces of them as things wear out, and that's one of the things we'll be talking about as we go through here. Oh, can I just bop back here and give just a funny thing? You're probably wondering what that map is. This is Chicago. This was my version of Chicago with a different zoning code that says no buildings within a mile of water. So the Des Plaines River, the Chicago River, or the lake, and everybody has to be a 15-minute walk maximum from open space. And the open space needs to be at least a mile across. So anyway, yeah, I don't really see that happening, but it's the idea that things could look a lot different, and things will look a lot different than they do today. So let's figure out how to get there. All right, here's our 5 deep energy retrofits, DER, deep energy retrofit, and why they don't make Phius. So we had a couple clients approach us saying, I'd like you to make my house net zero. The Frank Lloyd Wright house in the upper right, upper left, and the 2000 Suburban in Westmont in the middle bottom. And these are owners who just, they want to do this to find out what it takes and to set an example and to do something that's exciting to them and they feel like would be good. The 1970s ranch in the upper middle, he said, look, I really want a high performance house. I don't really need any certifications. I want to insulate. I want to put in mini splits. I want to do ventilation. What can we do? So that was like make it really good. And then my house in the lower right is a little farther along than this. We're getting into finishes finally. That I would like to have taken it to Phius, but I had some hurdles that kept me from doing it. So I said, well, could I get to Phius Source Energy? And the answer was yes. So that's that one. And then the Chicago 2 flat here was a client who said, we need to renovate. We bought this house. It's really nasty inside. It's been kind of, water damage, and the people who lived there were hoarders, and the place was terrible. We want to gut it and redo it. And we're like, okay, well, let's insulate it while we go. And they're like, fine. So we basically snuck in a deep energy retrofit. Now, even though they're not making the passive house metrics in terms of space conditioning, on all of them, we're planning and striving for continuous insulation. So, slab, foundation walls, above grade walls, window penetrations, roof, connecting everything. The same with the air tightness. We're using heat pumps for space heating and water heating. Most of these projects are all electric. We're planning for and incorporating solar PV, and we're using efficient appliances and lighting. So in other words, we're doing everything that the passive approach would do, but we're not necessarily making it to the retrofits now, or to the space conditioning metrics, and I'll explain as we go. The thing is that we're getting 70 to 100% energy reductions from where we found these projects. So we're getting to the 2030 targets. So this is where the disconnect can start to happen. And somebody will say, well, if I don't make the passive house metrics on my Frank Lloyd Wright house, that's okay. I'm making it net zero, right? So I think, yeah, sounds good. All right, so we'll start with my house. It's a little 1919 frame bungalow in Oak Park. When we came here, there was virtually no insulation anywhere in the house. We had about 10 air changes per hour at 50 Pascal pressure when you blower door it. It had an old gas furnace and water heater, gas water heater. Everything's kind of, tired. Only ventilation it had was a kitchen hood. Actually, it had an old-fashioned kitchen hood over the sink, which I didn't really understand. So we put a kitchen hood in because we like to cook a lot, and it was getting really, smell like mapo tofu for like a week. And high heat cooking is a thing, especially with gas. But and the exterior was in disrepair. The squirrels finally got in, and that's actually why we're here. They made it through the soffit, which was falling down, and the fascias were needing repair. So that's the state I was in when we found it. Over the years, I did a few things. I replaced windows before I knew anything about passive house. I put in double glazed, double hungs. They still got at least 5, maybe 10 years on them, so I'm not going to throw them out. And I spray foamed the roof. So I did a couple incremental things that kind of are getting in my way of getting as far as I want. But that's, that's what happens. That's the reality, is that sometimes you inherit a project as an architect or a builder or a homeowner who buys a home, which has some things that might make you think, I don't want to take this out right yet. So what I'd like to do is kind of just walk you through our energy modeling process on this house, because I've got all the data at hand, and then we'll be a little quicker on the other projects, but this can kind of show you what the big wins are in terms of looking at a house this size. So once again, with the energy model, the starting point, the way we bought the house, the way we found it was, an EUI, which is energy use intensity. That's BTUs per year of 113. It's a huge amount. We want to be in the well, we want to be at 0, but if we're in the teens, that's great. It needed a furnace size of about 100,000 BTUR to keep the thing warm. And if you look at the lower right picture, you can see where my gas meter used to be. And right next to it, after we stripped the siding off, you see that hole that somebody piled some bricks in? That's where they used to shovel the coal into the house. So we're going from coal to gas to electricity, and we're sealing it all up as we go. But anyway, like all these houses, that red bar for heating is that's where the energy waste is. And when you look at this picture of the siding, you can see, or what was underneath the siding, you can see why. There's no air tightness. There's a crack where the framing meets the foundation. There are holes everywhere. It leaks like a sieve. So, like I said, the first thing we did, insulation-wise, aside from just basic weather stripping that we could do and some caulk, was we spray foamed the roof. I made a huge mistake, and I spray foamed it with open cell because at the time, like 2014, I thought that was safer in terms of moisture diffusion. It would have been better to do closed cell from an air tightness standpoint, but live and learn. There we are. Nonetheless, it took my furnace size from needing 100,000 BTU/hour down to 65. Took my EUI from 113 down to 77. So you can see it's like a big swipe at the energy. And a lot of that is because I went from 10 ACH 50 down to 6. So I cut my air tightness almost in half. So that was kind of a big deal. And then I knew that the next things I needed to do were going to be difficult and expensive, like the exterior of my house. But when it got really bad and I had to replace it, that's when I decided let's do it, because the walls are the biggest opportunity in most houses. They're the biggest surface area, and there's a lot of leakage, air leakage that can come in through all those holes. So what we did here is we stripped it down to the sheathing, as you saw in that previous picture, and we wrapped it with this blue skin, this air tightness membrane. It's a peel and stick air tightness membrane. We taped it off to the foundation, and then once it was up and everything was sealed, we drilled holes and pumped in cellulose. And then after that, we wrapped it with this gold material that you see. That's a wood fiber board. It's a material called Styco. There's also Gutex, and my friend Alan Gibson in Maine is starting with his business partners a U.S. manufacturing of wood fiber board. So that's really exciting. It's a carbon negative material, and so as we start to talk about embodied carbon in the materials we use to retrofit, cellulose, wood fiber board, these are great. So that was the approach to the walls. We're going to get a lot more airtight. We're hoping that at the end of this, we're like at 2 ACH 50, and you see that red dial has gone now down to another 25% down. My furnace size now went from being 100,000 BTU/hour down to 26,000 BTU/hour. I mean, this is the big message, is like, you don't need a giant machine to heat and cool if you just keep the heat inside the building. So that's kind of passive house like fundamental, right? My red bar, my energy modeling is going down pretty good here. So you can see what we're doing with the energy modeling, why we're doing the energy modeling on these projects, so we can really understand, how big of a furnace we're going to need, and if we change the windows to triple glaze, what does that do? All of these factors to really get you to that sweet spot. The basement, it was wet and cracked and dusty and had no radon barrier and no moisture barrier. So even though it's not a huge energy savings, I couldn't stand the idea of leaving the disaster of a basement in the house that is, a building science problem and a health problem. So we tore it out, my son and my brother-in-law and a couple of high school kids and I, and put it in buckets and carried it out to a dumpster. I didn't need to go to the gym for a while. And laid down a couple inches of insulation, and then the Stega wrap vapor barrier, and that taped up to the wall the vapor barrier, and then we put this white, it's called InsoFast. It's an insulation membrane there. So we have total thermal separation from our new slab to the rest of the house. So this is like a passive house, right? The slab is now warm, it's air temperature, it's dry, or indoor air temperature. It's not conducting heat, it's not sucking in moisture. So I didn't get a bigger house, but I am getting a better house. I'll put it that way. So yeah, we're down below a 2-ton system for heating. This is great. And then I can switch fuel. So I can go from gas to electric. And getting rid of the gas line saved me $30 a month in taxes and fees. However, they did charge me almost $1,500 to take the gas service out, which was like a final, kick in the pants, goodbye, good riddance kind of thing. And they surprised me when they took it out, which is another funny story. But I gotta tell you, when that gas came out, it was really a visceral thing. It's like, wow, I don't have that dangerous, flammable thing that could kill me if I left my stove on. It really feels different when it's gone. So that was kind of cool. Now, one thing I will point out here, though, is when you switch from gas to electric, you'll notice that without solar, the annual energy cost goes up. So here, after I insulate and I'm still on gas, it's like $1,120 a year using, gas for heating and clothes drying and water heating. But when I switch that over to electricity, even with my efficient heat pumps, I'm paying $1,660 a year. So electricity is just a little more expensive than gas right now. And so the thing is, though, that when you go ahead and put solar on, then now we're down below 1,000. So that's where the magic happens, is that you get net metering and you sell power back to the grid. And now my EUI is down there where we want it, 11.5 EUI. I'm underneath the Phius source energy. And I'm feeling like this is a sustainable thing. It's pretty expensive, but I can afford it with where the cost of money is and where I had my mortgage rates and all that stuff. My, almost $150,000 into this house to do everything at once. New siding, insulation everywhere, some solar, rebuilding the back room, which was a thermal disaster. So anyway, that's kind of the process. When you look at the building section here, you can see, how we had some, insulation under the slab, wrapping up the foundation wall. We have a little bit on the exterior of the foundation wall, kind of capturing that thermal bridge. The yellow is the cellulose insulation inside the walls. And then there's the yellow fiberboard outside the walls. And then the pink is the foam insulation up above. So, yeah, so that's where we got. I am thinking about adding some more solar. I can almost get to net zero on the south side of my roof. If I added some solar to the north side of my roof, I could get to net zero, but I don't think it's a really smart use of my money or of solar panels. And I don't feel like net zero is necessarily where everybody should be. I think if we're really down at this low consumption level, we can feed our houses with renewable energy. I mean, that's kind of there's some math there that we can talk about later. But
hello.
Yeah.
Good.
So, sorry, we got somebody talking in here. So let me tell you a little bit about the next few projects. This is the Oscar Balch House, Frank Lloyd Wright, 1909. And like my house, it had almost no insulation. It had also about 10 air changes per hour. We did a pre-project blower door test. It had gas boiler for heat. And in last polar vortex, she was up in her bedroom where it's ringed with glass, and she couldn't get the furnace above she couldn't get the house above about 50 degrees. And so it was kind of, it was unlivable. So we knew that there was going to be an improvement in comfort as well as reducing energy use. So single glazed windows everywhere were a huge issue because they leak air as well as heat. And it has a rubble wall foundation, which is common for the era. The roof has these wonderful cantilevers, which are great for, shading and rain, but they're basically an air exchange mechanism. They're the opposite of a passive house roof. They let air come up through the house and just blows out the sides. So we knew we would have to deal with that too. So what we did, this is a very important piece of architecture, and being sensitive to historic preservation is, I think, extremely important. Frank Lloyd Wright is a design idol of mine, but even if it wasn't a design idol of mine, it's still an important building. And so principle of preservation is reversibility. So we wanted to use materials that wouldn't necessarily be spray foam, like sprayed on stuff. So we like to avoid spray foam for the embodied energy content. So we're using a lot of mineral wool on this, putting in new capillary breaks underneath the slab, the new slab, which has insulation underneath it, running capillary break up the inside of that rubble wall so we can put mineral wool in front of it and we won't have moisture coming in. The capillary break will direct moisture down to the new perimeter drain that goes through a new sump pump in the basement. So that basically gives us something in the basement running up the walls. We can get cellulose in the walls because the stucco needs to be redone on the outside. We discovered the original paint colors was a much more kind of gold, classic Frank Lloyd Wright prairie color, not the kind of grayish, brownish gray that it is right now. So we can drill holes at the stud bays and then patch them, and when we do our recoat, we can make it seamless. Now the roof was a different story. We can't tack insulation on top of this house and change the profile, so we did go to a spray foam solution there. And I just want to talk a little bit about spray foam. Some states like California require that if you're going to use closed cell foam, you have to use the HFO blowing agent instead of the HFC. HFC has a much higher global warming potential. It's like many times worse than CO2 when it goes up in the atmosphere and traps heat. So HFO doesn't. It's like the same as CO2. So it's really important to specify that. And like on my house, I asked the spray foamer to give me a cut sheet, and he gave me a cut sheet, and it was HFC. I said, I don't want that. I want the HFO. He vanished, so I had to find somebody else. I found Tom Decker of Chicago Green Insulation, who was fantastic, and sent me this fantastic sprayer, and everything just right. But anyway, here we used an adequate amount of closed cell foam to basically get our air seal and our condensation control, and then we just filled the rest with open cell, which is a little more benign. And we needed to fix the ceilings on the second floor anyway, and so we decided to just go ahead and take them down, put them back up, put new sand finished plaster, because the stuff that was there before was kind of cracked. A big part of this also was getting interior storm windows, which the contractor Von Driel Thurkson are just the best in vintage homes. They've done a lot of Frank Lloyd Wright. They built these, Adams Architectural Millwork in Iowa built the storms, but they all had to be kind of scribed and fit into each individual opening. They have these nice neoprene closures, so they're quite airtight. Made a huge difference in comfort the next winter. And so with all of these incremental improvements, these are not, passive house level insulation and air sealing. We're going to get to net zero with an 18 kilowatt hour solar PV. It's very, very close, and we need to finish our shading analysis. There are some big trees. But you can see from the energy modeling output here from Whoopi Passive that we're nowhere close on the heating demand. The passive house heating demand, we would have to be down below 8, and here we are at 23. This house is very sprawling. It's Frank Lloyd Wright, temporary. There's a lot of surface area. It's going to be very, very difficult to make that get down to that heating demand without tons of insulation. So yeah, it's a lot more comfortable, and it's historically, I think, going to be a sensitive and well done project. By the way, she, the owner, is running this on Instagram kind of as it goes, and this is a 5-year plan. We're doing this house for cash flow reasons. So Balch House, you can find on Instagram and see all these pictures of things, the geothermal system we're using for heating and cooling, et cetera. So let me check time and see how I'm doing. 5:35. Okay. The 1970s ranch was interesting. You know, it's a very different era. We think it has a vapor barrier under the slab, and it's got a nice concrete foundation, solid. But the only insulation on this project was a little bit above grade, and there was this really curious thing where you can see on the wall section here, the roof insulation was a little bit of fiberglass, but it didn't quite make it over the top plate. So there's this great pathway for heat and air. And, you know, there's fiberglass bats in the walls, and it just, you know, it's like, to me, it's like when we got post-war in this country and we had these great machines and we had all this fossil fuel energy, we could just like, you know, we could let houses sprawl and just throw energy at them to keep them, you know, keep them warm in the winter, versus what happened in, let's say, the 1800s, early 1900s. You had to make buildings compact because you had a little fireplace to try to keep warm with, you know, so it's a different mentality. And so what we're doing with passive houses now is more like, yeah, let's be compact. Let's be smart about the mass and the orientation. This house, you know, not so great for mass and orientation. It sprawls, it's a ranch, and, you know, it's got a big basement. It's all concrete. So, so our solution here was basically, you know, improve everything, but the slab, as we analyzed it energy-wise, didn't make sense to take out. It's a lot of embodied energy. You put a new slab in, you're going to use a lot of embodied energy. And when you look at the energy model, it's not a lot of energy that's going into the ground. The ground becomes a thermal buffer as you put energy into it. It won't be super comfortable, you know. It's still going to be kind of a cold slab, not without insulation underneath it. So you'll lose some energy there, but it's not enough to say, oh yeah, we should tear it out. But putting some InsoFast insulation on the inside of the foundation wall, easy solution to say yes to. Wrapping continuous insulation on the outside of the house, easy, good way to go. And then for the roof, we used targeted amounts of spray foam basically at the rim boards and the roof to get us some air sealing and a little higher R value under those short bits of space over the wall plate. You know, that's normally we like to do a raised heel truss of like 12 to 16 inches and get a lot of cellulose there. Didn't want to tear off the roof and rebuild it. So so you can see what we did there, just a little bit of spray foam. That holds the ventilation baffle in place, and ventilation baffle continues, and we put a, you know, 16 inches of cellulose up there. And then what we did for air tightness here was we basically wrapped the inside of the house with a membrane, an Intello membrane. It's one of those intelligent air sealing vapor retarders, or I'm sorry, air barriers. And so it gives us a nice clean surface. We can leave the existing drywall up on the ceiling, put the Intello over it, and then cross-furring so we can run the new electrical underneath the air barrier. So on this house, we could, you know, we're basically, again, only getting to like the you know, not getting near the heating metric for passive house, but we can get to well below Phius, the source energy limit, with just a 7 kilowatt array. And 7 is not insignificant, but it's not filling up the entire roof either. And so our question here was like, well, what would it take to actually get to passive house? And that's what this section is here. And so you can see the thickness of that exterior insulation, and tearing out the slab and having to do that. It's a lot of material, and The reason is partly because the shape of this building is not conducive. So, and you really can't justify financially the foam, the basement slab. You know, it's definitely going to cost more than a couple more solar panels. So anyway, we'll talk about this in the Phius adapted standard a little later on here. The brick 2 flat, how many of these are in the city, huh? Thousands, hundreds of thousands? I mean, so we took our guidance on this project from Building Science Corporation. They've got a lot of good stuff out there. 475 Supply has some good information out there too in terms of doing this foam free. We used spray foam on this project as well. But here again, we were into a you know, uninsulated house, wicking moisture up from the ground, and blowing it through the roof. So the owners wanted to lower the foundation, lower the basement. They had 3 or 4 boys, so it was like, we're going to have some space down here for wintertime boy activity. So so that gave us the opportunity to redo the slab. So we went ahead and if you're going to do redo the slab, yeah, for sure, put the insulation down there. We can get the drainage, get the sump pump, and it basically just ran enough insulation, closed cell on the inside of the foundation and the brick to get air seal and condensation control, which is about 2 inches. And then we stand a stud wall in front of that so we can run conduits, and then we fill that with cellulose so we get this sort of 2-part piece and not just rely entirely on the spray foam. We can easily get to the Phius source energy limit with a modest photovoltaic array, which will fit on the Chicago roof. And it's a pretty straightforward approach, you know. We would like to, you know, continue to study how we do this with less foam, but it gives you a fairly straightforward way to get quite airtight. Finally, the circa 2000 Suburban House. Now, this is an interesting one because this helps kind of talk about the issue of service life. This house is 21 years old. The furnace is got maybe another 5 years in it, or maybe it's about dead. The windows are definitely starting to fail. The siding was sort of a cheap cedar, and that's been woodpeckered to death, and it's kind of UV is starting to break it down. So there are a lot of surfaces and mechanical systems that need to be replaced. So the owner said, you know, what do you think? What do we do here? I'm like, well, I think you have a pretty interesting opportunity, because I think with a lot of people, like if your water heater is going to go out, yeah, you can replace it with a heat pump water heater. You may struggle a little bit to find a plumber to do that, and you need to run a new electric line to it, which is going to be a, 220 or 240. Get my 200s confused. But anyway, so you can do incremental things like that. Here, she's kind of doing it all at once. You can see that in 2000, this house hit 5.3 ACH 50, so it's better than mine and the Frank Lloyd Wright, but it's nowhere near where we want it to be. We want to be like at 1 ACH 50 for air tightness. But heating wise, we're at like 43 kilobtu's per square foot annual for the heating load on this house. We want to be, again, for passive house for this particular house, like below 7. So that's a factor of 6 times. So that's a lot. We know that we can do better. So our solution here was, since the basement had been insulated with stud walls and insulation, we're leaving all that in place. We're air sealing the rims with spray foam, and then we're going to basically do the same thing on this house that we did in my house. Strip it down at the sheathing, air seal it from the outside with peel and stick diffusion open membrane, put the wood fiberboard insulation, also diffusion open, and then new siding on top of that. And part of the idea with all this diffusion open is that we believe that the fiberglass bats that were used to insulate this have craft face on the inside, so they're doing some vapor retarding. We don't want to create that vapor sandwich. We don't want to put plastic insulation on the outside and trap moisture in that wall. We want to make sure it's able to breathe or dry to the outside. So we could barely get to net zero by piling solar on this roof. She didn't have much south roof at all, so we're basically doing it east and west. But it's basically a lot of insulation to take that base demand way down. I mean, if we look at the source energy, or let's look at the site energy before solar, we're going from 51 kilobTUs per square foot annual down to 12. So we're cutting the overall site energy use in, by 75% with the passive retrofit, and then offsetting the rest with solar. So this energy output here is before we've offset with solar. Attic was a little tricky because it was hits everywhere. So we're going to cellulose this, air tightness on top, and then lay down some foam board insulation. We like to try to find recycled polyiso from roofs to use basically, again, low embodied energy. All right, some wrap up here. So far on these projects, these are not addressing equity in the sense that we're going after low income. These are clients who basically have money to experiment. But I think that there's some good lessons to be learned for everybody, because the principles that apply on these houses apply to all residential buildings. And so I'm hoping that we're going to start building a library of case studies here. So yeah, these are clients kind of on a mission, and I'm really, really lucky to work for people like this, and I appreciate every one of them so much. The life cycle of equipment and surfaces definitely informs the plan. So if there's something that's giving out, if your exterior is falling off like mine was, take it off, insulate on the outside, put it back. If you have a beautiful brick exterior, don't do that. Maybe it's to the inside. So because not everything might need to be replaced, phasing can often make sense. We'll do the surfaces now, we'll do the mechanicals later, that kind of thing. As we strive for air tightness, we need to think about ventilation. So on all of these projects, we're introducing ERVs. So energy recovery ventilator, exhausting air from where pollutants are made, bath, kitchen, laundry, and introducing fresh air into bedrooms and living spaces. And then finally, I would just say that on all of these, it's important at the beginning to identify, is the goal net zero energy? Is it Phius retrofit? Is it Phius source energy? And that guides our decisions as we get into energy modeling. And there's a little bit of flexibility about that. I'm going to skip over that table. A couple summary thoughts. Some of the challenges that we run into. I would say you have to start with the end plan in mind, thinking about continuous thermal enclosure and mechanical systems, and then figure out the phasing. You have to know where you're going. Otherwise, you might do like I did on my house and put some big hurdles in the way that maybe you regret. So that's number one. Number two, boilers are an issue. So many buildings in this climate, in this city, in this region, are heated with boilers and radiators that run at very high temperature, like 180 Fahrenheit. You can't get that out of air source heat pumps yet. And even the ground source heat pumps need two-stage heat pumps to get you up to that 180 degrees. Now, theoretically, if you're losing a lot less heat because you've done this great retrofit, you don't need it to be 180, and you can work it with 140. But I don't know that yet, and so that's just an issue about heat pumps and going electric with your boilers. But this is the thing: if we want to be done with fossil fuels by 2030, you can't put in a gas boiler today because it'll still be around until 2040 something. So we've got to figure that out. You can switch out to an air system, but then you're taking out the boilers and you're putting in ducts, which we've done. It can be done, but it's just like this is an issue. Similarly, retrofit ERVs can be tricky. They can be invasive if you have to start running ducts everywhere. And so this is where, that was ducts with the T. And this is like, this ties into the boiler issue. If you're getting rid of the boiler and you're going to go to an air system, then you can hook the ERV up to it and all your air is traveling like that. That's what we're doing at the Frank Lloyd Wright House. Talked about this before, the sprawling shape makes the Phius metrics difficult. And buildings with poor solar access won't achieve on-site net zero. And that's okay. Make them efficient anyway, make them more comfortable. When you minimize waste through better construction quality, it's good for the climate, it's good for your comfort, it's good for building durability. We want these buildings to last and to be loved. So Phius has really started thinking about this, and Graham Wright, the chief scientist for Phius, just did a presentation last week, and I'm going to put it up in the chat here in a minute. It's on the Phius YouTube channel about how they're approaching the retrofit idea now. And it's really about zero carbon total. So in terms of embodied energy and source and operational energy, it's taking a longer view on carbon, and it's going to start allowing for phasing. The pilot program is about to open. So we're all kind of excited for thinking about how we can engage in this as a community and start to, build case studies. The advantages of certification are like all certified projects, the third-party review of the retrofit plan and the construction, so that you know you're getting something good. And this is, my calculations about how small my furnace could be don't work if the building isn't built right. And I've calculated I need, a 2-ton unit, but didn't get built right. You need a 3-ton unit. You can't get it above 60 degrees when it's cold, So the quality control is absolutely crucial, and that's, to me, one of the most important things about pursuing certification. The other thing is that there may be incentive funding coming down with new legislation that might require third-party certification. In other words, you don't just say, I'm going to do something good, give me some money. They want quality assurance. So that's something that we just have to kind of keep our eyes on as we start to move down this road. I think, prerequisites for any project should be improving the air tightness, developing an insulation plan that works in terms of building science, case by case, getting efficient mechanical systems, heat pumps using electricity, and possibly figuring out an embodied carbon limit so people aren't just using really high embodied energy materials to do retrofits, because that's still going to be kind of getting in our way. Finally, the stuff that I've been showing here is obviously involves a lot of work in the energy modeling. If we really want to scale up and be doing 600 of these a day, we can't be doing it like this. So the idea is if we can build a library of case studies now and techniques that you can quickly deploy with confidence, that's where we need to get to. And we also need an army of local tradespeople to implement these, people who understand, what it means to build a good enclosure and good mechanical systems and deploy it. So, Graham in his pilot program talk is talking about standardization and potentially even offshoring these things. You basically measure a house and say, I need these sizes, and somebody builds it in a factory somewhere and ships it over and installs it. So, we got to figure out systems for acceleration. And we'll probably need significant incentives for a lot of homeowners and landlords who want to do this stuff. I mean, I love this stuff, and it's getting old in my house. So that's that's how I'm seeing it. I'm sorry I kind of went a little bit long, but I'd be happy to take whatever questions there are. I'm going to stop sharing if I just find this, and we can open it up. All right. I'm going to roll up to the chat. Frank, I can read off your questions, but if you'd like to come on and talk, and we can go back and forth, I'm happy to do that. I'll give you a second to unmute if that's what you're thinking about.
You can read them. You can read them to start. You can read them to start. I'll do a follow-up question if needed. Thanks.
Okay, great. Sure. So, question first: are you able to or trying to maintain the existing 100 amp electrical service while performing the deep energy retrofit and electrification? Yeah, that's a good question, and I meant to hit on that. My house had 100 amp service, and I did a electrical load calc and found that I needed about 98 amps, and I hadn't calculated in the future electric car. So I did need to upgrade to a 200 amp, and it was expensive. And so that's an issue that I think we're going to have to figure out on a policy level. If people are going to spend, are going to electrify, and you have to spend another couple grand to take your panel from 100 to 200 amp, that's a burden to put on every homeowner or landlord. So yeah, other houses that we've found have had 200 amp service, or that we've been working on have had 200 amp. Well, the 70s ranch didn't, but the owner was an electrician, so he wasn't worried about that. Did you thermal image scan the existing walls from the inside after the cellulose was blown to see how well it filled the holes and gaps? I did, and we didn't find many problems. We were on the backs of the cellulose installers while they were doing it, but I am concerned about how dense they were able to blow, and this is something that I would say is really one of my biggest concerns on the project is that we want to see 3.5 pounds per cubic foot cellulose, so it's dense packed so it doesn't settle. I don't think they got to that, and they didn't know how to test it. There was a major, kind of communication difficulty on site. They blew it. We could see it coming out the top of the hole when they blow it from the bottom, and then they blow it from the top, and they say, okay, we got it, it's good. But I'm worried that maybe it's not. But it's hard to know where it's going to go. Next question: the sand and CO2 heat pump water heater generally can go up to 180 Fahrenheit or close to it. And the sand and CO2 is great because it doesn't use a nasty refrigerant, it uses CO2. And I think the issue with the sanding is capacity. I mean, how much water are you needing to move around, and how do you connect that to a boiler or a storage tank? But maybe the sanding can be used. Frank, do you know if people have been doing that for radiator replacement?
Occasionally they have, and Small Planet Workshop, which is West Coast, they are actually partnering with Sandon to create kind of a water drop system is what they call it, which is where they are banking multiple outdoor units with 1 or 2 indoor tanks, so that it's mainly more as a larger buildings, but a kind of a drop-in hot water plant replacement. So it can be done, but yeah, I guess as always, the first time is reducing the demand. But yeah, the Sandon is an option. There are a few other the Nova Arctic or the Arctic. There's a few other ones, but it is definitely tricky to get up to the 180.
Yeah, we did a project in Wisconsin. It's about to be finished certification as a Source Zero house, and we did use a Sandon water heater, and we used it for radiant in the slab, but the temperature in the slab, of course, is a lot lower. So, yeah, we really like that. Okay, but that's great to know. Thank you, Frank. I got to keep my eye on that. And this is the thing: technology is changing, and we just have to keep talking like this and keep on top of it. Mark's question on the brick 2 flat: when insulating the basement exterior walls with the closed cell foam, is there a need for a dimpled drainage material before you spray the foam, or do you foam directly to the brick? Yes, below grade, we do want that dimpled membrane so that, because moisture coming in has nowhere to go. It can't dry to the outside because the ground's always wet, basically, right? So above grade, we foam directly to the brick. Below grade, we foamed over a plate and membrane, which goes down to the interior drain tile. And again, taking all this from Joe Stebrick and Coda Buenos and all those guys at Building Science Corp papers about, you know, best practices. All right, what's the difference between Tyvek and Blueskin? Why choose one over the other? Tyvek is, we think of it as a weather-resistant barrier, so a capillary break, a way to get water away from your skin. Blueskin I think of as an air barrier and a weather barrier. Theoretically, Tyvek could be an air barrier, but I've never seen it installed to be truly part of an airtight enclosure. Tyvek, Blueskin is peel and stick, so it's sticky on the back. It literally sticks to your wall, and it's pretty thick. Now I can actually kind of rip through the Blueskin though, whereas Tyvek, you know how strong that is. Anybody who's trying to tear open a FedEx package. So anyway, I would choose the Blueskin over the Tyvek because I can get it to sort of wrap into to be, you know, to stick to the surface and give me a really good air barrier. Carlos says, thanks for sharing. For the two-story brick, what were the resources used? Building Science Corporation. And what was the other one? Oh, the other one that I mentioned in the talk was 475 Supply. So they're a supplier of passive house componentry and membranes and tapes and ventilators and skylights and all this stuff. And they have a ton of great information on their website that you can learn from. They have example details. And if you order their systems, they'll help you think through all of them. So it's great, like support for builders and architects and homeowners. All right, Lisa, thanks for sharing. You are welcome, Lisa. Thanks for sharing what you do. She's a solar pro. Okay, thank you. Oh yes, Frank, there are load share devices that can allow you to maintain the 100 amp service using the watt direct approach. And there's some information there. Yes, the load sharing device idea is that if you have a 100 amp service and you're going to be pushing it, there are some circuits you can identify that if they detect that you're going over your 100 amp, it'll, you know, shut off that heat pump water heater for now because something else needs it, you know, or it won't charge the car right now. It'll do something else. So I haven't gotten into that. I've heard about it. I was on an interesting presentation a month or so ago, and somebody was asking some electrical inspectors if it was permittable here in Illinois, and I think they said yes. So yeah, look up load sharing devices. I wish I knew more. Do you want to shed any more light on that, Frank, or are you still here? Yeah, there he is. Yeah.
I'll put a link or two into the chat.
Thank you. Thank you. Yeah, so that's all I'm seeing for questions. Did I miss anything? Anybody got anything? Jennifer, are we lined up for future presentations? Oh, first of all, this will go off to YouTube. Our Passive House Alliance YouTube channel is, we're just recording these and putting them up there. So I hope I didn't make any total gaffes or say anything wrong. What do we have booked here? We normally have our holiday party we're looking forward to at this time, and that's not really, these aren't those days. What do we have coming up ahead? Do you have calendar at all in front?
Not sure about December, and no problem. Not sure about December and the holiday party, but we are going to be having the Passive House 101 in January.
Great. Yeah. Yeah. New question from Carlos. I'm new to the group. What fix would provide the most bang for the buck when improving brick 2 stories in Chicago? You know, I would say that my take on that generally is take care of the roof first with air tightness and insulation. Because you think of the building as in terms of pressure, you know, you got high pressure at the top because warm air rises, you have low pressure at the bottom, and so it creates a stack effect, and so you're just sucking air up and out of the house. And the if you cap the top, you basically stop it from getting up and out. So that's usually the first place you get good opportunity for insulation and improving comfort. And then usually the next place is you deal with where it's coming in at the bottom. So sort of rim joists and door thresholds and all the little leaks. I think if I were to go back and look at most of the energy audits I've seen on houses, it would be first thing you do is air seal as much as you can with just caulk and, you know, the obvious gaps that you can see and you can just close up. And then, you know, weather strip your doors and windows because that's usually not too difficult or expensive. If you have, you know, big old historic double hungs, yeah, that's a big deal. But then, yeah, then working on the roof and then working on the basement. And then usually the next thing is look at retrofit insulation in the walls. A lot of people think one of the first things you should do is replace your windows, and it's usually way down on the list. It's very, very expensive, and if you have a decent window, you're going to go from you know, decent to a little better. Still terrible compared to a well-insulated wall. If you go, you know, if you have a terrible window, you can put a storm window on it for relatively inexpensive. But if you get a really good window, especially like a triple glazed window, you need to spend $600-700 on that. And you know, and your energy, unless you have a house that's all windows, your energy is not mostly the windows. So I just say watch out for that. Yeah, best bang for the buck is insulation. It's relatively cheap, and it does a lot, and it lasts, you know, a long time. But make sure it's installed well. All right. Another thing in the chat here from Frank, who is our out-of-town resource. I'm glad you made it and asked good questions. The Watt diet info. This is about load sharing. I'm just going to open up that YouTube video in my other screen so I have it to look at later. Cool. Well, I think that's it for November. I hope everybody has a great Thanksgiving, and I look forward to speaking to people soon. Eva, I see you up there. I know we've got an appointment set up. I'm looking forward to that. Neil, it's good to see you again. It's been a bit. Spencer, we're working on your project. Can't wait. The community here. So, oh, we got some new messages coming in. Just a thanks. All right, great. Thanks, everybody. I'm going to sign off and hope to see you in the new year, if not before.